Okay, let's start section 5.5. It's on the greatest common factor and factoring by grouping. This is really central. That's a really central skill in algebra. We'll use it for the remainder pretty much of this course, and it also plays a really large role in college algebra. So I'm going to start out with the definition, because everything in mathematics satisfies the definition, and the definition we try to make as precise as we can be. So the greatest common factor of two terms. So let P and Q be algebraic expressions. Remember, just regular integers like 7 and 3, as long as they're non-zero, they're actually considered polynomials, and hence algebraic expressions. They're constant polynomials. So then the GCF of P and Q, which is denoted by this type of, sometimes GCF is in all capitals, sometimes it's not, but P will be a specific number or polynomial, and so will Q, is another term, C, such that all three conditions are true. C divides P without remainder, C divides Q without remainder, and C is the largest term for which both 1 and 2 are true. So what does it mean to divide something without remainder? If I divide 20 by 5, I get 4, remainder 0. Sometimes we just say it evenly divides. So what I have is some of you were taught how to find the GCF of two integers by looking at multiples. Conceptually, that really is helpful. For example, if you wanted to find the GCF of 3 and 5, now I guess it's not multiples that you use. I'm not for sure how you're taught to find the GCF outside of a college course. I was thinking the least common factor or the least common multiple. So what I'm going to do here is show you my method to find the GCF, and I'll also show you how it can easily be transformed to find the LCM or LCD of two numbers. Some of you are still having problems finding the LCD or the LCM. So what we're going to do is I'm just going to show you. I think it'll be easier than actually going through those instructions, because those instructions you're just not used to reading abstract instructions. However, you need to be getting used to. So I say the first thing I do is I say, let's create a factor tree. So if you don't know what a factor tree is, you're getting ready to see one. So we start with one of the numbers, and not that. Clearly it's divisible by 2, so I divide it by 2 on one side. So 60 divided by 2 is 30. 30 is also divisible by 2. 30 divisible by 2 is 15. Now I'm done with my 2's. I got to think about something else. Well, 15 is divisible by 3, and 15 divided by 3 is 5. So what I have here, at the very end of these trees, at the very end, I guess the roots or the branches, is the factorization of 60. 60 is equal to 2 times 2, which is 2 squared, times 3 times 5. That's called the prime factorization of 60. The other is 40, and we're going to again make a factor tree. I just start dividing by the smallest obvious prime that it will be divided by. 40 divided by 2 is 20. 20 is also divisible by 2. That gives me 10. 10 is also divisible by 2, and that gives me 5. And these are my prime factors. I have 3 factors of 2. So it's 2 to the third times 5. So in other words, if you look at the very end nodes and you multiply them all together, you get your top node. 2 times 2 is 4. 4 times 3 is 12. 12 times 5 is 50. 2 times 2 times 2 is 8. And 8 times 5 is 40. So now what we do is I literally make a table. And that table is going to be determined by the prime factors that I found. So that's going to be the very first column. And then the second column head is just going to be one of my numbers. And the last column head will be my other number. Sometimes we have more than two numbers. This works for all of them. So here's what you do. You look over here and you say, okay, I have 60 has prime factors 2, 3, and 5. It doesn't matter how many 2's you have, or how many 3's or how many 5's, it's just distinct prime factors. So I have a distinct prime factor of 2. All of this is taken from 60. A distinct prime factor of 3. And a distinct prime factor of 5. All of those were just taken from 60. Now I look over here, and do I get any new prime factors? Well, I already have 2 in my list, and I already have 5 in my list. So I have all of the prime factors that appear in the factorization of both of my numbers. So now what I want to do is write some interesting information. So it's probably easiest to go down the column. So when I look at 60, I write how many 2's appear in the factorization of 60. Well, 2 appears twice, 3 appears once, and 5 appears once. And let's do the same thing for 40. 2 appears 3 times, 3 does not appear at all, and 5 appears once. So now you're ready to find the greatest common factor of 60 and 40. And that's going to be equal to each one of our prime factors raised to some power. So it's going to be 2 raised to some power times 3 raised to some power times 5 raised to some power. So really this table tells us what power we need to put in those boxes. So here is the answer. For the greatest common factor, write the smallest number in the row corresponding to each prime factor. So this is for the GCF. So for the GCF, our exponents, well, the smallest number in the row corresponding to my 2 is a 2. The smallest number in the row corresponding to my 3 is a 0. And the smallest number in my row corresponding to 5 is a 1. So the GCF is 2 squared, which is 4. 3 to the 0th is 1, so we can ignore that, times 5. So the GCF is equal to 20. So let's actually check to see if 20 makes sense. Is 60 evenly divisible by 20? It sure is. Remainder 0. Is 40 evenly divisible by 20? It sure is. And it turns out 20 is the largest such number for which this is true. I can't get any larger. There's other numbers. For example, 2 divides both of them. 2 divides 60 evenly. 2 divides 40 evenly. But there's a larger number that divides them. 5 divides 60 evenly. 5 divides 40 evenly. Oh, but there's even a larger one. 10 divides 60 evenly. And 40 divides 60 even. 10 divides 60 and 40 evenly, but there's even another larger one, and that's 20, and that's the top. There is no number larger than 20 that evenly divides first of them. So that's how you find the GCF of two numbers. This easily extends to polynomials. And here is just a side bonus. So once you figure out how to create these tables to find the least common multiple, or that's also known as the LCD, you do the exact same thing, except you do the opposite. Instead of taking the smallest number, we take the largest. So that would be 2 to the third, 3 to the first, and 5 to the first. So that's going to give me 8 times 3 times 5, which is 120. Because 8 times 5 is 40, 40 times 3 is 120. So using the same procedure, you can find the LCM. And that's all I'm going to talk about it. But just remember, if you get this table method down, just the slightest modification by taking the largest number in each of the corresponding rows allows us to find the LCM. Where do you use the LCM? And here's what I'm hoping everyone is saying: to clear denominators. That's one thing. The other thing is to add fractions. And those are very basic math skills. That's the reason I don't allow you to use a calculator. You need to know how to add fractions or subtract them, and you need to know how to clear denominators. So let's go back to our GCF. So that's the topic here, and let's do another example. And the nice thing about this is this method easily extends to finding the GCF of polynomials, or even the LCM of polynomials. So here we're going to do 27. So I know 27 is divisible by 3. 27 divided by 3 is 9. 9 is divisible by 3. 9 divided by 3 is 3. So it turns out 27 is equal to 3 cubed. And if you have the prime factorization of a number, you don't even need to use the table. This kind of factor tree is how you get the prime factorization. And I'll show you just how that's done without the table in just a second. Some people like the table. Some people want to do it as quickly as they can. And either way it goes, that's the reason I'm writing the prime factorization. So 30 again is divisible by 2. And 2 divided by 30 is 15. 15 is divided by 3. And 15 divided by 3 is 5. Now I realize there's different ways you can start off the division process, and it doesn't make any difference, because in the end you get the same exact factorization, and that's what we're after anyway. The numbers may be in different places at end branches, but the end branches are always going to have the same numbers. So 30 is equal to 2 times 3 times 5. So here we make our table. So I have my prime factors, then my 30 and my 27, and there's 3 and a 2 and a 5, so there's only 3 different prime factors. So here I'm just going to go ahead and, since you're learning, prime factors go in the first column. And remember, we don't care how many there are in the first column, but what the different ones are: 2, 3, and 5. Then for 27, and my 30 at the top. Now going down with 27, how many 2's are there? 0. How many 3's are there? There's 3. How many 5's are there? There's 0. Little m, actually almost done. Over here with my 30, how many 2's are there? There's 2. How many 3's are there? There's 1. How many 5's are there? There's 1. So again, the greatest common factor of 27 and 30 is equal to, so my factors raised to the power so take the smallest number in each corresponding row, so that's the 0th power, the 1st power, and the 0th power. So 2 to the 0th is 1, it disappears. If you want to put it up there, it's 1. 3 to the 1st is 3. 5 to the 0th is 1. So the greatest common factor is equal to 3. So how would you do it with just the factorization? So I have 27 is equal to 3 to the 3rd. And I have 30 is equal to 2 times 3 times 5. So what you do is you look at the common factors. And in this case, the only common factors in the list of 27 and 30 is 5. I said 5. I said 5 looking right at 3 is 3. And here is where this method causes confusion. To get the greatest common factor, you take the smallest exponent. And that's where so many people go astray. So again, we can verify that 27 divided by 3 is 9, and 30 divided by 3 is 10. And that's it. There is no number larger than 3 which divides 27 and 30. And we're talking about non-trivial factors. Clearly, every number is divisible by 1. It's a trivial factor, we don't care about it. So here you should try to do the remaining 2 on your own. And once you get used to what you're doing, then you can develop your own method. So I have 15 and 29. So 15 is divisible by 3 and 5, but 29 is prime. That means the only factors of 29 are 1 and 29. So how do we proceed? So I'm going to give you an important fact. This is a theorem. I'm just going to call it a fact, though. So the greatest common factor of 2 integers, I'll say positive, is always less than or equal to the smallest of the two numbers but, here's the but, greater than or equal to 1. That tells you the GCF of two integers always exists. So what I know is the GCF of 15 and 29. It's always less than or equal to the smaller of the two numbers, which is 15, or it's greater than or equal to 1. So here are two more facts. And then I'll come back to it. Additional info. If one or more numbers so if one or more numbers in the list is prime, then the GCF is equal to 1. 2. If the smaller of the two numbers evenly divides, that means divides with remainder 0, the larger then the GCF is the smaller of the two numbers. And these are really helpful facts about the GCF. So let's review them one more time. When we're talking about just numbers now, positive integers, because when we talked about polynomials, there isn't really a sense of larger or smaller, except by means of degree, and that somehow it's the same, but this is really restricted to integers. So the GCF of two or more positive integers is always less than or equal to the smallest of the numbers in the list, but it's greater than or equal to 1. It's never 0, never 0. Sometimes we will want to take the negative of the GCF, but that's another story. We don't have to. If one or more of the numbers in the list is prime, a prime number is a number that is evenly divisible only by 1 and itself. Then the GCF is 1. You're done. You cannot get any greater than 1. If the smaller of the two numbers evenly divides the larger number, then the GCF is the smaller of the two numbers. So using those facts right here, I just discovered that the GCF is prime, has a prime in the list, that 29 is prime. So I just discovered the GCF of 15 and 29 is equal to 1. Because 15 is going to have, you're going to have 3 in your list and 5 in your list, and 29 will have 0 3s and 0 5s. So we don't count the numbers themselves or 1 as prime factors in our list. So the GCF is going to be 3 to the 0th times 5 to the 0th, which is 1. Here's an interesting question for you. What is the GCF of 4 and 28? Well, you don't need to do anything, because you already know that the GCF of 4 and 28 can be no greater than 4, but it has to be greater than or equal to 1. Since 4 evenly divides 28, then the GCF is, in this case, actually the largest it can possibly be, which is 4. And one last example. So a lot of this is just gearing you up to learn how to factor. So let's find the GCF of 33 and 22. Well, let's do it another way. 22 is equal to 2 times 11. 2 is prime and so is 11. 33 is equal to 3 times 11. So what common factor do they share? They share a common factor of 11, so I ignore the 2 and 3. And what's the smallest power of those 11s? Well, they both have a power of 1, so it's 11 to the first power, so the GCF is equal to 11. And you would find that exact same answer if you looked at the whole factor tree method, and you would quickly discover that the factor tree is pretty sparse in branches, and there you would have 2, 3, and 11 as your prime factors. 33 and 11, not 33 and 11, but 33 and 22. 0, 3, 1, 1, 0, 3, sorry, not 1, 0, 1. So anytime a row has a 0 in it, you can just ignore it. So the GCF is 11 to the first power, which is equal to 11. So now we're going to extend this concept to monomials. And it's really easy. Monomials in a single variable whose constant term is 1. Super simple. To find the GCF of 2 or more monomials in a single variable whose constant term is 1, consider the exponents on each monomial. Then the GCF of the monomials is the variable raised to the least or the smallest exponent of these variables. Whoops. So the GCF of x cubed and x to the 5th is equal to x cubed. I just take the smallest exponent. And clearly x cubed divides both x cubed and x to the 5th. X cubed divided by x cubed is 1, and x fifth divided by x cubed is equal to x squared. So in this case, a remainder 0 means a power that is greater than or equal to 0. So here I could write this is x to the 0th, because that's equal to 1, and our power is greater than, exponent is greater than or equal to 0. Here our exponent is greater than or equal to 2. You don't really have to worry about this. This is really the simplest part. This is the simplest thing you'll ever do in this particular class. You just can't get it mixed up with other things, because if you were looking for the least common denominator or the least common multiple, you would take the larger of the two. But we're looking for the greatest common factor. We have y to the 4th and y squared. And we take the smaller of the two. So finding the GCF of two algebraic expressions, part 1. To find the GCF of two algebraic expressions, find the GCF of the constant terms, then find the GCF of each variable. The GCF of the algebraic expression is then the product of these GCFs. So really, this is really quite simple. So I'm going to take, and lots of you all don't need these formal rules. It seems like the GCF is something that everyone gets. Well, that's equal to the GCF of 8 and 4 times the GCF of x squared. Well, 4 doesn't have an x term. So if it doesn't have an x term, you could either write x to the 0th, which is 1, or you can just skip it all together. It's just the GCF of 8 and 4. The smaller of the two divide the larger. So I know the answer is no greater than 4, but always greater than or equal to 1. And in this case, since 4 divides 8, it's 4. So that's the GCF of those two terms. Now let's find the GCF of these three terms. So again, one of the rules is, when you're looking at the variable, here's an x. If an x is not included in every variable, if that variable is not included in each term, every single term, I don't have to worry about it. Y is not included in every single term. So really all I have to do is find the GCF of 20, 10, and 35, and multiply it by the GCF of the one variable that appears in all three terms, and that's x. We have an x cubed and an x squared. And I already have an x cubed, I don't have to repeat it. Well, this side of the calculation is really easy. It's going to be x squared. So I have to find the GCF of 20, 10, and 35. So I can already tell you it's probably going to be 1 or 5. So again, we're just scribbling this out. Let's do this both ways. So 20, I'm good. Or am I not good? There we go. So 20 is equal to 2 squared times 5. 10 is equal to 2 times 5. So literally, since 10 is a factor of 20, I can really just consider 10 and 25. Let's go ahead and do the whole thing. 35 is 7 times 5. Wow, well the only common factor that they all have is 5, and that's raised to the first power. If we were doing the table, I would have 2, 5, and 7. And clearly, any row that has a 0 in it, I can just ignore. So it's going to be 5 raised to the smallest of these numbers. So it's 5 raised to the 1. So the end result is the GCF of these three terms is equal to 5 times x squared. So let's do this one. It's going to be the GCF of our constant terms, 7, 21, and 35, times every term has an x, so I have to consider the x terms, the GCF of x cubed and x squared. I don't need to write that third x cubed, I already have it there. Does every term have a y term? Nope. Does every term have a z term? Yes, so I have to consider the GCF of the z terms, so that's z squared and z. So this is the easiest part. You just take the smallest power. So the variable part is going to be x squared times z. What's the GCF of 7, 21, and 25? Well, we have a prime in here. So the only thing that we have to deal with is I guess I need to amend that one rule or put them in a priority. Yeah. If one or more numbers in the list is prime, then the GCF is 0 unless number 2 below is true. And in this case, let's go back to it. I love having this humongous writing space. Never run out of paper. So 7 is prime. So it's either going to be 1 or 7, because I already know that the GCF is going to be greater than 1 or less than 7. So the only way it could possibly not be 1 is if 7 divides both of the larger numbers. And 7 divides 21, because 21 divided by 7 is 3, 35 divided by 7 is 5. So it's 7. So the GCF is equal to 7x squared z. Okay, now we're going to factor out the GCF. So it's really not difficult, and some of you just have an intuition on how to do that. Some of you are just absolutely freaking out because you're barely keeping your head above the water. And that's the reason I'm kind of trying to explain a procedure that you can capture and repeat. And for those who feel really, really confident of how to do this, you can listen into part of it. And if you get tripped up later on, which you might very well do, you can come back and listen. So this is example 10. So we're going to factor out the GCF of 8 squared plus 4. And what is factoring? Let's review really fast the distributive property or distribution. So if I have A and I multiply it by B plus C, that gives me AB plus AC. So factoring is when you are given this side of a distribution equality and we want to go over here. So the GCF of these two terms is going to be A, so I can pull A out, and the other two will be enclosed in parentheses with either a sum or a difference in between them. So the first thing we do now is we find the GCF. This is two terms. This is term 1 and this is term 2. The GCF of all terms. That's the first thing we do. So we want to find the GCF of 8x squared and 4. Since only one of those terms have an x squared in it, all I really care about is the GCF of 8 and 4. And now my little theorem is really helpful. I know that my GCF of 8 and 4 is going to be greater than or equal to 1 or less than or equal to 4. It's going to be equal to 4 if 4 evenly divides 8. And 8 divided by 4 is 2. So I'm done. It's 4. So here starts the thing. I write my GCF on a line by its own, and then I put parentheses there. Then I look at my original equation. 8x squared divided by 4 is the same as, so over here on the side or in my head, I'm doing 8x squared divided by 4. Well, that's 2x squared. And then I look at my plus 4, and I divide it by my GCF term, and I get plus 1. And I have factored out my GCF. So it's 4, written a little bit more compactly, 2x squared plus 1. And this is called, we have factored out the GCF of 8x squared plus 4. So as long as the GCF of year 2 terms here is greater than 1, then this factorization will always be a non-trivial factorization. By non-trivial, I mean it means I'm not just enclosing the whole entire thing and putting a 1 in front of it, because that's always true, right? The GCF will actually be some number, and that number, when you factor it out, will change each of these terms. 8x squared divided by 4 becomes 2x squared. 4 divided by 4 becomes 1. Okay, so let's look at this. It's the GCF of both terms, so the GCF of 5 and 2 times the GCF of, not the GFC, what did I write there? The GCF of my variable terms. My variable attached to each term, y and z to the 4th. Well, these two, y and z to the 4th, I don't have to worry about it. I need at least a y. They have to share a y or share a variable. And here, I know that the GCF is going to be equal to greater than or equal to 1 or less than or equal to 2. Now 5 and 2 are both prime, so the default is it's going to be 1 unless 2 evenly divides 5. But if the whole entire list is prime, it's always going to be 1, and 2 does not evenly divide 5. 5 divided by 2 is 2 with remainder 1, not remainder 0. So the GCF is 1. So there is nothing to be factored. This is a case that the only thing I could do is put parentheses around it and put a 1 right there. And we don't need it. We don't need to do this. Just simply say it cannot be simplified. I don't know what my math lab will ask you in your multiple choice there. But you can't do anything to it. It cannot be further factored. So here we have 617 x cubed y squared minus 34 x to the 4th y squared. The problem is 617 prime. Well, I'm going to show you what you do. I know you're dying to grab your calculator, but the calculators normally don't tell you if a number is prime. Let's just get our formula. This is the GCF of 34. Don't worry that it's negative. And 617. Now, if 617 is prime, and it's not, that means it cannot possibly be divisible by 34, then we're done. The GCF is equal to 1. So the question is, does 617, if it's not prime, does it share any factors with this? Now I'll show you how to work that out. Then look, this has an x squared and an x to the 4th. So let's just write down the answer. The GCF of those two terms is going to be x to the 3rd, and then y squared and y squared. So all I have to do, they both have the same power, is find this baby right here. So let's look at 34. 34 is divisible by 2. 34 divided by 2 is 17. So all I have to do is check. Is 617 divided by 17? Well, we can try to do it. All we have to do is check one thing. It's 617 divided by 17. So I'm going to take a guess that 4 is going to get us, 40 is going to give us close. 680, too much. 30. 21, 2, 5, 10. So 17 will go into 60 3 times. And 3 times 17 is 51. And that's 107. Is 107 a multiple of 17? Well, I know 17 divided by, I know that 510 divided by 17 is 30, so I know the answer here is going to be greater than a 0. Well, let's try it. 17 times, let's try 5. It's going to be almost there. 5 times 7 is 35. That's 85. If I add another 17 to it, it's going to put me over. So no, it's not evenly divisible. So this is going to be the GCF is equal to 1. So this is our greatest common factor is x squared y squared. So let's do that. So we can factor out x squared y squared. I'll put my parentheses here. So here we go. What is 617 x cubed y squared divided by my GCF? Well, the y squares cancel, so it's going to be 617 x cubed divided by x squared is x. What is my 34 x to the 4th y squared divided by x squared y squared? Those cancel. It's going to be minus, this is a minus, x squared. And that is the factorization. X squared y squared, 617 x minus, that can't be right. I did something wrong, because I can still factor out an x. X third. Did I write something there? Notice how I just caught my mistake. Oh, yeah. It would help if I wrote down the correct GCF from above, wouldn't it? So this x vanishes. I just redo everything I just did, except I have to divide it by the correct GCF. And this is going to be divided by x to the 3rd, so I'm going to have just a power of x there. There we go. Why did I know I'd made a mistake? Because my terms in the center, in the parentheses rather, they both shared a factor of x. So that tells me I could not have possibly factored out the correct GCF, and that's a good check. And indeed, I looked up and I saw that I copied it down wrong. So this is just simply 617 minus x times x cubed times x squared. Oh, this is minus 34. Caught another error. Talking too much, getting excited because it's almost over the lecture. Yeah, I mean right here clearly that's 34. Minus 34. Minus 34 x to the 4th divided by x to the 3rd is minus 34x. We got it. Okay. So what's the next one we have to do? Okay. In the class, students always scream at me if I make a copy error over. Here it's just me and the cat. And the cat doesn't scream at me. Let's see if we can just find out the GCF. So 64 and 8. Those are my two integers. So I know my GCF is either going to be less than or equal to 8 or greater than 1. Does 8 evenly divide 64? It does. 64 divided by 8 is 8. So my GCF of my constant terms is 8. X to the 5th, x to the 3rd, I take the x with the smallest power. Y squared, y squared. Well, they both have the same power. So now what I do in my head, 64 x to the 5th y squared divided by my GCF. Well, 64 divided by 8 is 8. X to the 5th divided by x to the 3rd is x squared. Y squared divided by y squared is 1. So 8 minus 8 divided by 8 is minus 1, and I'm not going to bother to write the 1. X cubed divided by x cubed is 1. And y squared divided by y squared is 1. So I have to write the 1 because I can't put a 0 there. It's never 0. It's always going to be at least 1. So writing it more compactly, this is our answer. And you can always check your answer by distributing the terms. In other words, when I reverse the process and I do distribution, I will get my original polynomial. And that's, if you're ever in doubt, just reverse factor. Use the reverse process. Use distribution and see if you get your original term. So here I have minus 3x cubed y plus 2x squared y minus 5xy. So let's do this in our heads. 3, 2, and 5, that's a list of prime numbers, so the GCF is 1. So x cubed, x squared, and x, the smallest of those three. If you want to put a 1 there, that's fine. It's 1 times x. So the smallest exponent of those is 1. Y, y, and y, they all share the same. So it's 1 times xy, but you don't have to put the 1 there. So now I divide minus 3x squared y by 1. Well, minus 3 divided by 1 is minus x cubed divided by x is x squared. Y divided by y is 1. So I move to the next one. 2 divided by 1 is plus 2. X squared divided by x is x. Y divided by y is 1. Then minus 5 divided by 1 is minus 5. X divided by x is 1. Y divided by y is 1. So this is one way. This is one way. And normally it would be written as xy minus x squared plus 2x minus 5. But your book, and this is completely subjective, and so if your book doesn't count, if your MATLAB does not count this right, then I would write them a letter. Of course, don't tell me to write them a letter, because there's nothing I could write them that would change anything. They're set in stone. They're not changing anything. But your book may want you to factor out, don't know, factor out a minus 1. Now, to factor out a 1, you don't do anything. If you're given a list of terms and to factor out a 1, all you do is put it in parentheses and that's it. But factoring out a minus 1 is different. So to factor out a minus 1, what we do is, let me erase this here because I'm going to be writing over it. So factor out a negative 1. Factoring out a 1 is nothing. I'm going to factor out a minus 1. So I'm going to take that minus and I'm going to put it in front of my x, y. And then all I have to do is really no work, is just change the sign of each term. X squared minus 2x plus 5. Why would they care? I have 2 minus signs and 2 plus signs. Here I have 2 minus signs and 2 plus signs. So it's a matter of convention. Both of these are correct. Now, depending on the context, one of these may be better than the other. But as a general rule, if the only thing you're asked to do is factor it out, I would stop right here. This is perfectly fine. The authors of the book may have some different philosophy with respect to that, yet I would argue with them on it. And we kind of have to do what my math lab wants us to do because I'm not able to write paper versions of an exam because I won't see you in the classroom this year. Well, let's do this. So minus 9, 5, and 7. Well, 5 and 7 are both prime. So as soon as you got a prime there, as soon as you have two different primes, you're done. You know it's 1. But 5 doesn't divide 9, and 7 doesn't divide 9. So if you want to put a 1 there, you can. We'll put a really light 1 there. For those who, for some reason right now, just feel more comfortable with it there. Now I look at all my x terms, and I take the smallest exponent, which is 1. Now I look at all my y terms, and I take the small exponent, which is y. So xy is my GCF. So minus 9x to the 4th y squared. So minus 9 divided by 1 is minus 9. X to the 4th divided by x is x to the 3rd. Y squared divided by y is y. Plus 5 divided by 1 is plus 5. X squared divided by x is x. Y squared divided by y is y. 7 divided by 1 is 7. X divided by x is 1, y divided by y is 1, and I'm done. So this is equal to xy times minus 9x cubed y plus 5xy plus 7. Let's factor out a minus 1. So I just put a minus in front of my GCF. And then I just change the sign of all of my terms. So factoring out a minus 1 is really simple. And in the context, depending on the context, it may be something that you would need to do. So our last objective, this is a long lecture. Our last objective, I think our last objective, yes, our last objective is to factor out polynomials by grouping. So here I have 2x minus 5 minus 3 times x minus 5. So the question is, here's my first term. here's my second term. Do they share a common factor? Well, the GCF of 2 and 3 is 1, but then I have an x minus 5 and an x minus 5. So they share a factor of x minus 5. So I can factor out an x minus 5. So 2 times x minus 5 divided by x minus 5 leaves me a 2. Minus 3 times x minus 5 divided by x minus 5 leaves me a minus 3. Now I can simplify. So this is x minus 5 times minus 1, or minus x minus 5. And that's it. That's all it is to do that one. In this case, the minus would need to be, the constant term always has to come at the top. Let's do three more. This is really important lecture, though. I feel like it's gone on a long time. I'm saying it's probably, if we were in the classroom, I would have had to cut the explanations for some of those. So a b minus 6a plus 2b minus 12. So here is what we do. This is factor by grouping. So what I do is I group these into two groups where there's a common factor. In the AB and the 6A group, we have a common factor of A. And the nice thing about these is they always write them down for you grouped already. It's either the first two and then the second two, or there's none at all. And in my second group, there's a common factor. What's the common factor in 2 and 12? Well, it's always greater than 1, greater than or equal to 1, less than or equal to 2. When is it equal to 2? Well, when 2 divides the larger of the two number. So this is a common factor of 2. So what I do is I factor out my common factor of A here. Let me do a different color. So I take in my first grouping, I take out my factor of A. AB divided by A leaves a B, minus 6A divided by A leaves me with minus 6. Over here I factor out a plus 2. So I write a plus there. 2b divided by 2 leaves a b. Minus 12 divided by plus 2 is a 6. Are we done? No, we're not done. Lo and behold, look. I went from 4 factors to 2 factors. This is 1 factor. So I went from 4 terms to 2 terms. This is 1 term, and this is another term. And these terms have a common factor of b minus 6, because b minus 6 is in both terms. So a times b minus 6 divided by b minus 6 leaves me an A. 2 times b minus 6 divided by b minus 6 leaves me a 2. And look what we just did. This is really important in mathematics. We went from a sum, this is a sum of terms, to a product. If you could only realize fully just how important that can be in mathematics. So we went from a sum of 4 terms to a product. So the main operation here is plus and minus. Here the main principal observation is multiplication. Something's wrong here. Oh, that's supposed to be 2, not A. Sorry. No, that was right. The A was right. So A times B minus 6 divided by B minus 6 is A. 2 times B minus 6 divided by B minus 6 is plus 2. So that was what it was. I just wrote A. Well, they look kind of the same. Good enough. I mean, it's not good enough. It has to be A. So let's do number 18 and 19. Yeah, these are kind of wild. Factoring always presents problems for students, and our only answer to you is practice makes perfect. And you literally got to practice. So we have x cubed. This is factoring by grouping. And when you're asked to factor by grouping, you already know that they've been grouped in such a way that it's going to work. So we start out with grouping. We have to do groups of 2. So the greatest common factor of x cubed and 5x squared is x squared. So that's my greatest common factor in the first grouping. X cubed divided by x squared leaves me an x. 5x squared divided by x squared leaves me a 5. Over here, the greatest common factor of 3x and 15 is just 3, because there is no x term down there, and it's plus 3. 3x divided by 3 leaves me an x. 15 divided by 3 leaves me a 5. So lo and behold, I've reduced it now to 2 terms, but these 2 terms share a common factor of x plus 5. So I pull out the x plus 5. X squared times x plus 5 divided by x plus 5 leaves me an x squared. 3 times x plus 5 divided by x plus 5 leaves me a 3. So again, I went from a sum of 4 terms to a product of 2. And the last one. I just have to scoot this down here until I can write it down. So this is 19. M squared n squared plus m squared minus 2n squared minus 2. So this is a great example. So again, it's going to be factor by grouping. It says factor by grouping. So you make a grouping of the first 2. The greatest common factor of m squared n squared, and m squared is just m squared. So m squared times n squared divided by m squared is n squared. And m squared divided by m squared is 1. Now the greatest common factor here, let's just go with the common factor of minus 2. Now you said, well, maybe it was supposed to be positive, but let's do a minus 2. Because there's a minus 2, and right there's a minus 2. So minus 2n squared divided by minus 2 leaves me with an n squared. Minus 2 divided by minus 2 leaves me a plus 1. Well, how nice that is. Because now I have another common factor. If you had not factored out a minus 2, you would have minus n squared. You would have minus n squared minus 1. And you'd have n squared plus 1 over here. So you'd have to think, oh, if I factor out a minus 1, I will get what I need. You'd have a plus 2 here minus n squared minus 1. So we did the right thing in factoring out the minus 2, but it's clear to see that there's a minus 2 right there and a minus 2 right there, so let's do it. So in the last step, I went from 4 terms to 2 terms, but these 2 terms here share a factor of n squared plus 1. So n squared plus 1 divided by, m squared times n squared plus 1 in parentheses divided by n squared plus 1 just leaves me an m squared. Minus 2 times n squared plus 1 divided by n squared plus 1 leaves me a minus 2. So that's some pretty amazing stuff, because again we went from a sum of 4 terms to a product of 2. And that is indeed it for 5.5.